Thank you. So yes, as somebody pointed out, I have an interesting date. So one of the very nice things I've discovered about having postdocs around is that they compensate for my general technological ineptitude. So I've been copying the same slides that Asher wrote for me for however long it was since Asher was a postdoc at Connecticut, and I just erased the old slides and write in some new things. Apparently, I forgot to change the date, though. Very good. So I wanted to I wanted to say something about the topic that I'm talking about today. So this is mostly old work that I did, or a reversion of some old work that I did with Rod many years ago that I sort of thought at the time that I would never talk about. So we're going to get to a theorem about ordered abelian groups called Hahn's theorem, which is a very nice structural result, but it's a somewhat technical piece of ordered group theory. And at the time, I was very interested in looking at it because I thought it was going to be a little bit more complicated than ACA naught. So I thought it was going to either require the existence of an omega jump or maybe the existence of the nth jump for every n. And I thought, sort of looking at the classical proof, that it was going to be a nice example that bumped up just a little bit higher. And so Rod and I worked on it. And in the end, it turns out that it's equivalent to ACA naught, which we'll see at the end. And so that made it somewhat less interesting. I mean, I was happy that somehow we seemed to have to simplify the proof a little bit to get it to work and all. But then to have a very technical algebraic theorem that was another example of an equivalence with ACA naught seemed, I don't know, less interesting and something less likely to be talked about, right? So why am I talking about, why am I going to talk about it today? So, so the reason comes from the work that Julia and Karen Lang have done over the last number of years towards understanding the MorganSarah theorem. So MorganSarah proved that every real closed field has an integer part, and in Julia's talk earlier, she mentioned a lot of the algebraic pieces that go into this proof. And right, the general algebraic method there is to take the real closed field and embed it into what looks like a much more complicated object, these Hahn fields. But the embedding has some advantages in the sense that you have some extra structure in this Hahn field that lets you then conclude stuff about the field that you started with, right? And this method of sort of doing this embedding into these big algebraic spaces that you can represent as generalized series and things like this gets used in a lot of other places. So in particular, in ordered abelian group theory, Hahn's theorem is sort of the analog of this MorganSarah construction, right? And so sort of what my goal today, and the reason I picked this sort of technical kind of piece to talk about, is to sort of show how this analog works. And in particular, I guess as Matthew said in the last talk, right? When you're dealing with fields and with groups, in some ways, fields can be nicer because you have a little more structure theory there and all. On the other hand, sometimes groups are nicer because they're a little bit easier to sort of build by hand. Sometimes there's fewer operations to worry about. So in this context, the groups are actually a little bit simpler to work with. And so in particular, we can use this work to answer one of the main questions that Julia and Karen have been working towards, but we do it in the context of ordered groups rather than real closed ordered fields. All right, so that's the plan and the goal. So let me just say at the beginning, like a couple of, in case anyone hasn't seen this, right? So an ordered abelian group is just an abelian group together with a linear order that satisfies the sort of obvious condition you want. If x is less than y, then x plus z is less than y plus z. And one of the reasons why I wanted to go ahead and mention the definition in its entirety is just to point out, because this will come up later, that if you take an ordered group and you just flip the ordering over, it's still an ordered group. So you, and that's a process that we're going to do later on. On the other hand, you have, right, the similar axiom for an ordered field, and you can't do that with a field. So one of the consequences of the axioms for ordered field is that one has to be positive. So you can't flip things upside down. Okay, so in order to sort of build up, so what I would like to do is sort of talk about some of the algebra that falls on the real closed field side, and the sort of analogs on the ordered group side, right, to build up and say why these results are sort of the same, what the analog is here. So I need a little bit of sort of just very basic algebra at the beginning. So throughout G will denote an ordered abelian group, which I'll sort of assume is computable, although everything I do is uniform. It could all be done relative to G. R will denote, again, a computable, say, real closed field. So in either case, we have the notions of two elements being Archimedean equivalent, or one element being Archimedean less than another, which are just the standard notions. And I'll use either sort of square brackets x or w of x, the weight of x, to denote the equivalence class of x under the Archimedean equivalence relation. And if I have a set of elements, right, w of a set, the weights of the elements in that set are just the set of Archimedean equivalence classes represented by the elements. And the last thing I wanted to point out as I get started are, since we can effectively pass from an ordered abelian group to its divisible closure without changing the Archimedean classes or anything, it doesn't hurt throughout this all to assume that the group is divisible. So you don't need that for Hahn's theorem and the things I'm going to talk about, but it doesn't hurt. But just to point out, right, with the fields, it is important that these are real closed, right? So in general, the existence of things like integer parts don't hold for all fields. You do need this closure property there. Okay, so the first section, so there's sort of two pieces of algebra that we're going to need to put together to do this. So the first on the real closed field side is what's called the value group, right? And it's what it's being used to do. So I'll put that thing here. It's just being used to describe the Archimedean classes. Right, so in a real closed field, if we look at the Archimedean classes, they have the natural structure of a divisible ordered abelian group. So the group operation of addition just corresponds to the field operation of multiplication. The identity element in the group is the equivalence class of the multiplicative identity in the field. And then I'm going to start off by sort of ordering the equivalence classes by saying the class of x is less than the class of y if x is Archimedean less than y. Because this seems like a natural way to think about it at the beginning, and we're going to do something different later as we go along. Right, and just to point out a couple, so for example, why is this group divisible? So in a real closed field, you can take nth roots of positive elements, and so this corresponds to being able to divide by n in the field and so on, or in the value group. Right, so the point is that this group is just describing the algebraic structure of the Archimedean classes. And it's often useful to work not just with the value group, but with a copy of the value group inside the field. So if you take an embedding of the non-zero elements, the weights of the non-zero elements, into the multiplicative group of the positive elements of the field that picks out an element of each equivalence class, the image of that is called a value group section. So it's just a copy of the value group inside of R. And so to give an idea of some of the steps that have gone into Julia and Karen's analysis and starting to work towards understanding this Morgan-Sarah theorem, right, they showed that if you have a real closed field, it has a value group section, which is delta 2 in the field. And you can't do better than that in the sense that there's a computable real closed field such that every value group section computes 0 prime. So you can't do better than delta 2. All right. So so let me mention one last thing. So there's the definition of the value group again. So I'm going to do this later, but just to point out now, so when you study valuations of ordered fields, right, an algebraist would flip the order that they put on the value group. So they would order the Archimedean classes in the sort of opposite way that you'd think. So they would say the class of X is bigger than the class of Y if and only if X is Archimedean less than Y. So I didn't do that in the original definition because it makes it a little harder to think about at the beginning, I think. But you'll see why I'm going to have to do this later, and you'll sort of see why I have to do it later. I will point that out. But again, the point just is you can flip the order on the group over, and it doesn't change anything. All that's happened there is it's more convenient to turn the order over. All right. So what happens on the ordered group side? So the role of the value group, the sort of value object now is a linear order and not a group. So if we look at the Archimedean classes in an ordered abelian group, now they form a linear order, and there isn't any other sort of natural structure on them. So again, we can look at the weights of the non-zero elements or the positive elements. It doesn't matter which one. And I'm going to, again, order them in this sort of natural way at the beginning, although later we'll flip this upside down. And again, it's useful to work with copies of this linear order of the Archimedean classes inside the group. And so you can just fix embeddings to pick out representatives of each Archimedean class. And so a very simple result that Rod and I did, and as part of this analysis for Hahn's theorem, one of the first very simple steps is to just say, oh, you can have a set of Archimedean representatives that's delta 2, and you can't do better than that in the same way. And I should say, right, this is considerably, well, it's considerably simpler than the work that Julia and Karen did, right? I mean, for example, the fact that it's delta 2 follows almost by definition, right? So I'm going to go on and say something. Absolutely. So the coding, the example here where every set of Archimedean representatives codes 0 prime is definitely presentation dependent. So, but you can say, so if you want to get something that's presentation independent, you can say something about that. So, for example, right, if you start with, so you might say, okay, I want to start with the linear order and just build my group around that. So as long as the linear order you start with has an RE presentation, now you can build a computable ordered abelian group such that the ordering on the Archimedean classes is isomorphic to L. And now, in any, this is an invariant of the isomorphism type. So now in any computable copy, any set of Archimedean representatives is going to be isomorphic to Al. And that means, so now an old result of Feiner's that said there's an RE presented linear order with no computable copy tells you that you can at least get computable groups G where no computable copy has a computable set of Archimedean representatives. Yeah. So you can at least say something about presentation independent things here. All right. So that's the first sort of object that goes into this analysis, this description, sort of algebraic description of the Archimedean classes, and the value object is either I guess I should have said here, the value group is an ordered group or just a linear order in the context of ordered groups. So the second thing that goes into it is on the real closed field side is the residue field, and this, so here, this describes say the elements, the reals that are in your real closed field, right? And how does it work? So in your real closed field, right? You've got 0, you've got 1, right? You've got all the infinite sort of elements falling out here. You've got the things that are the sort of infinitesimal elements, maybe sitting sort of down here, right? And so you can look at the subring that consists of the elements that are either in the same Archimedean class as 1 or are in a strictly smaller Archimedean class, right? So there you're looking at the collection of finite and infinitesimal elements. And on the other hand, inside that ring, it has a unique maximal ideal, which is the set of infinitesimal elements. And if you take the quotient of those, you get what's called the residue field. And the point of that is we've forgotten for a minute about the infinite elements. We've just looked at the ones that are finite or infinitesimal. We mod out by the infinitesimals, and so what are we left with? We're left with sort of the reals. And to say that a little more precisely is just to say that the residue field now turns out to also be real closed. It's an Archimedean field, so it's isomorphic to a subfield of the reals. So if you think about that subfield of the reals that it's isomorphic to, that's the residue field. Okay, so it's just giving some sort of description of what are the reals that this real closed field is sort of built around in some sense. Okay, and again, you can look at an embedding of this into the field. So a copy of this that actually sits inside of R is called a residue field section. And again, Julia and Karen, looking at this piece, they showed that every real closed field has a residue field section, which is pi2 inside it. Right? So you have to say some sort of maximality conditions. This is roughly why the pi2 comes into play. And furthermore, that's the best possible. So you can build a computable real closed field such that no residue field section is sigma 2. And that sort of, more or less, that comes about by thinking about descriptions, right? Inside the residue field, you have to have all of, well, actually, let me leave. So, yeah, all right, let me leave that. I'm going to leave that for now. Otherwise, I'll run out of time. All right. So I'm going to come back to say what the analog of the residue field is in the ordered groups setting in a little bit. So notice that here, so in some sense, to make sense out of this, right, we needed to have this element 1, right? 1 now, the field is playing an important role here, and we don't have an obvious thing that plays the role of 1 in the groups. And so, okay, so I'm going to come back to what plays the role here. But there is something that plays the role here, and again, it's going to exactly describe sort of elements of R inside this ordered group. It's going to play a very similar role. Okay, so let me see. All right, so now let me say something about Hahn's field. So Julia talked about these on Monday, and right. So here I'm going to do it in a slightly more restricted setting, just in the setting that comes up here for what I sort of want to do. So I want to start with let K be an Archimedean real closed field. So you could do this construction with any field. Right? In particular, Julia was looking at it with real closed fields or algebraically closed fields. So here I want to start, though, with an Archimedean real closed field K and a divisible ordered abelian group G, and just let T be an indeterminate to write my power series, general general series in. So the Hahn field consists of the formal series of this form, where we're taking the sum over a well-ordered subset of the group, and the coefficients, so the a sub g is a non-zero element of the field. And then t sub g is just, well, to mark where it came from. So here the point is to make clear. So alternately, you could just represent these elements as functions from g into k such that the support of f, so the elements from g that aren't mapped to 0 in k, is well ordered. Right, so the elements are really, this is, the elements are just these functions from g into k that have well-ordered support, but it's useful to write them as series because we are going to add them as series, which corresponds to just adding the functions component-wise, right? But we can also multiply them now as series. So the multiplication is just as you would normally multiply series. And the fact that the supports are well ordered makes that well defined. All right, so those are the elements of the Hahn field. And so there's a natural order, again, that you can now put on this Hahn field using the fact that I started with a real closed field, right? So a field with an ordering on it. So I can order two series by looking at the least place where the coefficients differ. And so when I write that, just to be clear, right, if you think about these things as functions, right, you can also think about these series as having values for every term t to the g. It's just you put zeros in all the values that aren't in the index set. So when I really say compare them, I mean treat the coefficients as 0 if g is not in the index set, right? Right, so that, again, that seems like the natural ordering to put on there, and of course it's defined because the supports are well ordered. All right, and so when you do this, what you get out is a real closed field with residue field k, right? So this is exactly what Julia was talking about. This Hahn field, as long as we start with a real closed field and a divisible ordered abelian group, will come out to be real closed in the end. And k is in fact the residue field. All right, so let me just point out. So let me work a little bit farther on what happens with the Archimedean classes here. So I ordered these sums. Right, so now I've got two sums. So I've got one that looks like a g0 t to the g0 plus a g1 plus da 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 da. Right, it goes on. Right, it goes along some ordinal. Right. So what determines the Archimedean class of this element of the Hahn field? So it's this piece right here. So to avoid my having to take absolute values, right, assume that this coefficient, say, is positive, right? But this is the term that that determines what the Archimedean class is, because if I started with the term that's just 1, or here, right, g0 is less than g1, I should say, right? I'm doing these in order. Right, if I start with this term here, the fact that the k is an Archimedean, so now I'm going to use the fact that it's an Archimedean real closed field, says that if I multiply this by a big enough n, I get above 1 gets above here. Right, so this becomes bigger than that. And again, of course, if I multiply this by a big enough n, I'm going to get bigger than here as well, because it's from an Archimedean ordered field. So this is the piece that determines the Archimedean class of this element. And if I look at two series, when is it that one is going to be Archimedean less than another? So I claim that the series with the A sub g coefficients is Archimedean less than the one with the B sub g if the least element of the S0 set is greater than the least element of the S1 set, right? So the point is, if I had another, BH0, the B series that started over here, and it started at some H0, which was actually less than G0, then the corresponding term in A has a 0 coefficient, right? So no matter how many times, right, no matter how many times I multiply this by n, I'm not going to get bigger than this because it's a 0, right? So it's Archimedean less. All right, so all right. So what does that all say? So what it says is if in the value group, remember we're looking at, so think about now the value group of this Hahn field. So where the elements of the value group are the equivalence classes of these, the equivalence classes of the elements of the Hahn field. So the equivalence classes of these sums. And so if we want to have if we want to order those in the natural way that corresponds to turning the value group of the Hahn field into G, you should order it with this flipped ordering. This is why I said I would come back to this in the end to explain this piece. Right, so we want in the value group to say the equivalence class of the sum over the S0 index is bigger than the equivalence class for the one over the S1 if the S0 term is Archimedean less than the S1 term, right? And the point is that makes the order agree with the G order on the least elements of the index sets. So the point is that the map now that sends the Archimedean class to the least element of the index set is now an order isomorphism from the value group onto G. So this is just to explain why in all of this things get flipped over as they will later on. Right. So as I said, if you follow the standard conventions for looking at valuations for real closed fields and order the Archimedean classes in this flipped way, then the Hahn field is a real closed field with residue field K and value group G, just like you want. Right? And of course, you could leave things the way that you could leave things without flipping the group order. Then you would have to define the Hahn group in terms of sums over index sets that were anti-well ordered. And that seems, I don't know, that seems unpleasant, maybe. Anyway, that's the reason why. Okay. All right, so all of this was getting to say something about this MorganSarah theorem that had to do with integer parts in real closed fields. So, right, so Julia gave this definition on Monday as well. So what's an integer part of the real closed field R is a discrete ordered subring I that has the property that every element little r of the real closed field is pinned between I and I plus 1 for some little I in the integer part. And here, to be a discrete ordered subring just means that 1 is the smallest positive element in I. Okay. Right? And so that tells you, in fact, that in this condition for being an integer part, the little I is unique. There is one, and so it's automatically unique. All right. So MorganSarah proved that every real closed field has an integer part. And what is there? I mean, what is the proof in the barest outline looks like the following. So start with little k being the residue field of your real closed field. They constructed a value group section. So that's just a copy of the value group sitting inside of the real closed field. And a truncation closed embedding from R into this Hahn group. So notice this Hahn group at least has the right form. It has the right residue field. It has the right value group. And in fact, you can embed R into it. And what truncation closed means just is if you have a term like this one that's in the image of the embedding, and you can chop it off at any point, get rid of this end segment, and this well-ordered initial segment of it still is in the embedding. So that's all truncation closed means. And the point of that, which I'm not going to write down the definition, but the point of that is that if you take a truncation closed subfield of the Hahn field, it's very easy to write down a definition of the integer part, right? So you write it down in, anyway, you just look at the form of the elements and you can tell whether they're in the integer part or not. So you can now take the image of R in the Hahn field, find the integer part in a trivial way there, and pull it back to the real closed field. And that's the way their proof works. All right, so Julie and Karen have a bunch of results about the complexity, sort of algebraic complexity, computability theory complexity of this construction. And so, for example, they can say things like there is a computable real closed field that has no NCE integer part. So they have some nice diagonalization techniques. They can talk about what this embedding from R into K of H looks like. Right, bounds, as Julie was talking about, bounds on roots, lengths of series to get roots and things like this. But two things that are unknown, right? So one is it's unknown whether you can do this in ACA naught. So, for example, and in other words, if you can do it sort of with a finite number of jumps. So you certainly can't do Morgan-Sarah's proof as it's written in a finite number of jumps. They definitely use information that takes you up into the hype hierarchy, right? But could you massage it a little bit? And I mean, as I said, when Rod and I started on this project, we thought, or at least I thought, we were going to need an omega jump, all right? And we did a little bit of work, and we didn't. All right, so can you get it down to ACA naught? Or even more, it's unknown whether every computable real closed field has a delta 2 integer part. So it's possible that they sit all the way at the level of delta 2. All right, so those are the two questions that I want to say now. I want to flip and look at the group case now and answer those two questions in the group case. Okay. All right, so I want to switch now from the Morgan-Sarah theorem to Hahn's theorem. And I'm first going to sort of state it in a classical version to avoid the mess of doing things in reverse math. And then I'm going to at least give you a taste of the mess that goes into doing it in reverse math and coding things up and go from there. So I said Hahn's theorem is a similar embedding theorem with a similar proof. So we want to switch from real closed fields to divisible ordered abelian groups, where again, divisible is not important, but it doesn't hurt. The value group gets replaced by a linear order. So the value object goes from being an ordered group to just being a linear order. To represent the structure of the Archimedean classes, and the residue field is going to be replaced by some Archimedean ordered abelian groups, and you'll see exactly what these are in a second. And so to state Hahn's theorem sort of in a nice, clean kind of classical way, and to use another structure theorem about ordered abelian groups, that says every Archimedean ordered group is isomorphic to a subgroup of the additive group of the reals. So when the analog of the residue field now is going to be some Archimedean ordered abelian groups. Those are themselves all isomorphic to subgroups of the additive group of the reals. So again, they're talking about elements of R, and so I'm just going to use R and to put the biggest group that there could be in there for now. Okay. And I'm going to try to write things. I'm going to write things not the way I would originally have written them, but I'll write them in the way that matches the Hahn field notation. So if L is a linear order, then the summation over L of copies of R is just the abelian group of all functions from Ln to R under component-wise addition. So there's no ordering on this or anything yet. It's just a group. All right, so a Hahn subgroup of this collection of functions from Ln to R is just a subgroup of that abelian group that has the property that if we take any function f in H, the support is well ordered, right? So it's exactly the analog of the functions here. And moreover, to be a Hahn subgroup, the H needs to be closed under these cutoff functions. So if I fix an element of the linear order and I fix a function in the Hahn subgroup, and I take the function and I chop it off somewhere, the initial segment is still in the Hahn subgroup. So this cutoff function is just saying do exactly this. And maybe there, maybe I write this down, right? So the point is now you can write these in exactly the same way. So each element of H can be represented now in this sort of series form, although you don't need to now because we're not using the series to do multiplication. But it can be represented by a series in the same kind of way over well-ordered index set. And the cutoff function, again, is just exactly that picture. You can throw away n segments of any function, and you have to stay in the subgroup. And this is exactly, so the requirement that H is closed under these cutoff functions is exactly the analog of being truncation closed from MorganSarah. All right. And then, of course, we can order this in exactly the same way that we did. F is less than G. If and only if we compare them at the least element where they differ as functions, right? Exactly what we did before. And so, as before, if we flip the ordering on the equivalence classes when we're thinking of these as value objects, then the map sending the equivalence class of F to the least element of its support is an order isomorphism from the Archimedean classes onto L, right? So again, it's making the Archimedean representatives exactly have order type L. Okay. So what does Hahn's theorem say now? So it says if G is an ordered abelian group, and I take a set of Archimedean representatives, which I order in this flipped way, then G is in fact isomorphic to a Hahn subgroup of the set of functions from A into R. Right? So now it looks, anyway, there is a truncate. The other way to say that right now would be to say there is a truncation closed embedding from G into the set of all the functions with well-ordered support, ordered in the natural way, right? So this is saying exactly what the MorganSarah theorem said, right? And so it's a generalization in this sense of Holder's analysis from the Archimedean case. All right, and so to say a little bit about what happens with reverse math, so I'm going to say a little bit about the sort of ugliness involved, just to also to give something about the structure and draw out a couple more analogies. But right, if we want to do this, study it effectively or in reverse math or something like that, we want to replace the reals now by some sort of countable Archimedean groups that we can write down and handle in nicer ways. And of course, we can always recover this sort of version by then embedding those things back into R, which you can do effectively. All right. So here's sort of a crack at doing this. So if you have a linear order A, and I'm going to fix, so for each A, I'm sort of going to think about this. All right, so I've got a linear order A, and sort of above each point in A, I've got an Archimedean ordered group. So I have a sequence of Archimedean ordered groups indexed by A. So a Hahn subgroup now of the sum of these groups Ka. So again, think about these as though they were all sitting inside the reals. So a Hahn subgroup of this sum, indexed by some index at I, is just a sequence of functions. And what should the functions do? So they should be functions from A into, okay, the union of all of these groups. And the value at a point A of the function, right, f of A is just going to pick out some element of this ordered group, k of A. And it should do it in such a way that the support is well ordered, so it's the right type of function, and that these functions are closed, they're a group, so they're closed under addition and the inverse operation, and they're closed under these cutoff functions, right? So it's just a, anyway, yeah, it's just a fancy way of writing this down. And then to say in something like reverse math that G is isomorphic to a Hahn subgroup of this sum is to say that there is a Hahn subgroup like this that's actually indexed by G, where the indexing gives you the isomorphism, right? So what happens, so the function indexed by the identity element of G should map everything to the zero element in the Archimedean ordered group Ka for each A. And if we want to add the function indexed by G and the function indexed by H, that should be the function indexed by G plus H, and so on and so forth, right? So this is just giving us a way of explicitly saying we have a copy of G given by these particular kinds of functions. All right? So now you can state this in a version that you could actually look at in reverse math. So for every ordered abelian group G, there's a linear order A and a sequence of Archimedean ordered groups such that G is order isomorphic to a Hahn subgroup of this space. And now we have it written down in a nice way in second order arithmetic. And this is the statement that turns out to be equivalent to ACA naught over RCA naught. All right, when you do that. All right.
What
Yeah.
exactly made you think that it could be higher?
So it's the proof. Yeah, so the way the proof works, I'm going to say something about this in a minute, but the way that the proof works is you start by embedding a sort of a small group, and then you extend this embedding one element at a time. But as you do that, you define a bunch of auxiliary algebraic objects. And on the face, these auxiliary objects sort of look like they're each using a jump. And they're kind of piling up on top of each other. And so the thought was, as you looked at it, it looked like you were using a jump each time, at least one jump each time you did a sort of a one-point extension, embedded one more element, or really the Q closure of one more element. And that they were actually piling up. So that's why. And you'll see in a second sort of why that, I'll be able to say why that doesn't happen. But that was the reason. All right, so in one direction, for like to get ACA out of this turns out to be sort of not very difficult. So if we have elements of G, looking at the least elements of the supports of their images tells us exactly where they sit in Archimedean classes. So you play around with that to get some nice examples where you can actually calculate those things, and you code ranges of functions, and it falls out without too much work. So how do you prove Hahn's theorem in ACA naught? And so again, well, this will say something about your question, but it will also point out the sort of the last piece that goes here that I haven't exactly said what it is yet. So, very good. All right, so we start with our divisible group G. We fix a set of Archimedean representatives. So let me just sort of note, there's a jump right there. For each element from the set of Archimedean representatives, we look at two subgroups. The subgroup of elements that are Archimedean less than or equal to A, and the subgroup where they're strictly less than A, right? That looks just like what do we do with that? We take a quotient, right? That looks just like the residue field construction, right? So that's, so once we've picked the Archimedean representatives in each Archimedean class, we can do something that looks just like the residue field bit. And we get, I mean, just for algebraic nonsense, these groups are convex, they're divisible. So the quotient is Archimedean, which means it's really a subgroup of the reals. And moreover, this is a place where it's nice to have taken this assumption about being divisible. Since the smaller of these groups is divisible, it splits off as a direct summand. So in fact, this group K of A, which right, there's the sequence of dot groups, that's the analog of the residue field sections. And there's not just one, there's a whole sequence of them, right? And they can differ. So you can split that piece off, and that gives us the analog. And so going back to Julia and Karen's result was that the residue field was always pi 2, and that was the best possible. It couldn't be sigma 2. So here, these things, you can get these as well in a pi 2 form. Although I have not written down all of the details, I am quite confident that you can also do the diagonalization. So mainly because in doing the diagonalization with the residue fields, the facts, all the algebraic facts that Julia and Karen used were facts that followed from the O-minimality of real closed fields. Ordered divisible abelian groups are also O-minimal, so we have all the same algebraic facts sitting there. So anyway, morally I believe that result holds as well, although I will say I have not written down all the details to see that. So then it remains to do the construction to construct this Hahn subgroup. And as I said, so it's done by, you start by just, you take the divisible subgroup just generated by these K sub A groups, and then the things that weren't in the subgroup generated by that, you add them sort of one at a time. Right, and the reason why we could get this to all work in ACA not is that we could fix all of these groups and this information up front at the beginning and not have to generate it as we went, which is how the original construction went. All right, but just to point out one thing about it, again, to fix the Archimedean representatives is roughly a jump. To define HA and HA prime are CE and co-CE respectively, but if we want the whole sequence of them over 0 prime, all right, we're up at 0 double. The KAs are pi 2, we're up another couple of jumps. In doing, I believe we use another jump as we actually do this embedding. Anyway, so to do this, you're up somewhere at the level of 4 or 5 jumps. All right, so I'll come back to that, the reason I mentioned that in a second. So finally, to sort of close this circle, right, the idea was to say something about integer parts, the analog of integer parts in a group. So what should we mean by an integer part? Well, the idea would be, say, just fix a positive group element and treat that as though that were the one element in the integer part of the field. So if to define an integer part in G, fix a positive element little g, and then say that a subgroup I is an integer part of G relative to little g. If I sub G is an ordered subgroup, it has G as its least positive element, so it's discrete ordering, and it has the right sort of integer property. All right? And just because, again, as the method of the Morgan-Rousseau is getting the integer part, once we have this truncation closed embedding from Hahn's theorem, we can just read off what the integer part should be. So we can get that these integer parts exist in the group case in ACA not. Right? But as I said, the proof of Hahn's theorem used several jumps, so it wasn't clear, could we get a delta 2 one? And so Karen and I looked at that for a while, and at first we tried to do something to lower the number of jumps we needed in Hahn's theorem, and that didn't seem very fruitful. So instead, Karen suggested we try sort of a method that I gathered didn't work in the Fields case of just sort of building it up directly from below, right? Forget about using this embedding at all. Groups are easy enough to work with that you can just maybe build it up from below. And so sure enough, that's what we did. And so you can, in this context, always get integer parts relative to any positive element G, which are delta 2. And you do it in a different way. And so on the good side, right, in some sense, this says that there's some hope for the field questions to be done in ACA naught or to be done in a delta 2 way. On the other hand, the method that we did to get delta 2 definitely doesn't work in the field case, or doesn't seem to work in the field case, and it's there's more the sort of steps in the MorganSarah construction as you're doing these extensions seem a little more complicated than the Hahn's theorem case. And so it's unclear how much this analysis is going to help, although it's also too early, I guess, to say that it won't help. All right, so I will end there. Thank you very much.
Mm-hmm. That you were going to use it. That's what you can't do that in fields. Mm-hmm. So the fact that you could do that says already that the choices of things to put into an integer part aren't going to interfere with each other so much. It seems as if it's
Yeah, so you have a lot more freedom for, in fields you have a lot more interaction with the choices that you make. When you put something into an integer part, you've said not only stuff about its Archimedean class, but also its, so if it's an infinite thing, absolutely, it's square root, yeah, absolutely, yeah. So this is, yes, the field case is definitely more complicated.
How many jumps do you need? It's ACA naught.
I don't know. I did not count them exactly because it's somewhere around 4 or 5. But my guess is that you can get that down if you're a little more careful about things. But we didn't see a way to say get it down to 1. Which was why we sort of started doing something else, because we were sort of really interested in delta 2 versus just ACA naught. But yeah, I don't know exactly.